they tell the Kafka that, hey, I have processed this message. Okay, so the next time the consumer actually pulls for new events or messages, the Kafka looks at the offset message and then sends the next events. So this way, like we can ensure that we are always reading from a given point of time or given point in the data queue, right? So the commit offset can be synchronous and or asynchronous. Okay, so it depends on how you want to implement it. So there are like trade-offs, right? Say if you want it to be synchronous. Synchronous is the by default behavior. So what it essentially means is whenever you are trying to set the offset to a particular partition, the consumer waits for the acknowledgement from the Kafka. Like this is actually set to this partition, right? But if you are using the asynchronous part, what it does is like it just fires like, hey, offset is here, and it doesn't wait for the actual acknowledgement. So you will never know if it was actually acknowledged or not. So there is a possibility of reading the same message again, but then you wouldn't wait for the acknowledgement message and just continue to process. So if you have your consumer if your consumer is idempotent, right, then you can use the asynchronous keys because it's always, for example, you are processing data and pushing it to ClickHouse, and then you have set your ClickHouse engine to remove the duplicates, right? Then you don't really care, like if you read it again. The asynchronous makes more sense in this case, right? So yeah, the next part is rebalancing, the process of redistributing partitions among consumer instances in a group. So is rebalancing. So essentially there are multiple reasons you would have to rebalance. Okay, for example, say as we were discussing the synchronous part, right? If the consumer disconnects from Kafka for some reason, right? So Kafka waits for the consumer to acknowledge, and if it doesn't in some time, then in a set time it triggers a rebalance. Okay, so what rebalance does is it takes the consumers and then assigns the partitions between them in a very efficient manner, like, right? You have to make sure that all the consumers are paying attention to all the partitions rather than only a set of them. So here is this thing, right? So producer needs to know this case, right? So what happens is when there is a rebalance triggered, right? We pause the consumers, like whatever partition are. So there are two: the previous group of consumers, and the new group of consumers. So until the previous group of consumers are finished, new group won't come in, right? But producer is still pushing to partitions. So now the producer knows in the new instance, like these are the partitions I need to push, right? So that's how we actually manage it, right? So the producer needs to know like where it needs to push, because otherwise, say it in the rebalancing, before rebalance there is a state of Kafka where it is pushing to partition P1. After rebalance, it is pushing to partition P2, right? So in that instance, we need to make sure that all the messages from the previous instance are actually consumed before we start on the new one. But the web service never stops pushing it to Kafka. Okay, so it is always ongoing. And then so which is producer is kind of straightforward, right? So you look at the event metadata or the data itself, and then you choose where to submit, right? Or where to put it across the topic or partition. The consumer is a bit tricky. Like it can be approached in two ways. One is a thread per consumer model, which comes out of the box. So if you have implemented Kafka, say in Java, then this is the model like it offers, the Confluent. And then the second part is multi-threaded consumer, right? So what it essentially means is like you are going to use multiple threads to process the jobs actually, not the read. So what is thread per consumer model? So essentially it revolves around infinite loop. Okay, so there are two actions: retrieve the records and then process the fetch records. right? So you process and commit offset and then you retrieve. So this is like an infinite loop where you are processing messages continuously, right? So very straightforward, little pitfalls, but this does not ensure efficient use of your resources. Okay. Next one, yeah. So this is like a measure diagram for this. Essentially, poll and process record. That's it. Right. So multi-threaded, right? So multi-threaded is bit different. Like we still have the first part of it, where your first main thread is actually reading, or the what we call a poll loop. Okay, it fetches the records from the Kafka, and then instead of itself processing, what it does is it spawns a pool of your thread workers, and then submits the jobs to them. So now instead of only one guy working, you have as many threads as you want, like working on it. So so the actions are like pulling the messages and delegate the task to threads, confirm that tasks are completed, and then commit to the main queue. So yeah, here it is, right? So essentially there is a main thread, this poll, create and submit tasks to these threads, and then ensure that all the tasks are completed, and then once they are completed, commit the offset, and then this continues. So it's just a pseudocode I have written. So essentially, if you look at this part, right? So there is create and submit tasks, check for active tasks. So essentially, what the check active task does is it makes sure that the tasks are completed, and then you commit offset. And the last part, right, like push failed messages to DLQ. So DLQ here stands for what we call dead letter queue. Okay, sometimes what happens is the events you receive are malformed. So if it was actually HTTP web server, you just return 400, right? But since we are processing it later, after acknowledging it, right? So we might run into these cases, and we don't want to lose these messages, right? Like our customers or your customers might want to know what went wrong in this case, right? So what we do is we take the messages of failed like the errored out messages, and push it to a new queue, new topic called dead letter queue. That's it, right? Like and we can then later on fetch the records to analyze it, and then maybe improve your consumer code, or maybe let your customers know like why it actually failed. So it's mostly to post-mortem, like why it failed. Okay, so this is a basic what you say processor. Okay, so essentially the process is you read and process the messages, wait for completion or some helper methods, and then it's basic one. So this is the main one. So if you remember, like once you read the messages, right? So you need to group them by partitions, because you need to ensure that the message you fetched are actually processed in the order we have received. And that means the messages from the same partition need to be processed one after one. Right? So we just group them by, and that's like executed, I guess. This is again a small part. So one is it checks for active tasks. If you are running it in thread pool, there is a very straightforward method, right? And then once you have ensured that all the tasks are completed, you commit the offset, right? So so any questions till now?
Yeah, what's the number of days the message stays in the dead letter, if it is not processed?
It's actually configurable, right? Like each of the, you can configure it, but the thing is, if you are using a managed Kafka, so the storage cost might rise, so you might need to process it, say, in a couple of weeks. So for us, we keep it for 14 days, and before 14 days, we just export it to a manageable storage and then process it from there.
The default is 14 days.
Yeah, the AWS one gives default is 14 days.
Okay. And what's the number of partitions you can create? Is there a limit? It depends on the Kafka framework.
There is no limit actually, but if you create more, say, so there is always a trade-off, right? Like if you create a lot more, then you need to manage a lot of them, and then spawn more consumers, more resources. So it's kind of you just like decide on the usage. Like if you think you are gonna use you're gonna need so many partitions, then sure. There's technically no limit. There is I saw somewhere like there was 4 billion something limits on the partition on a very large cluster, but then again like never confirmed it.
This Kafka is hosted on the Confluent or is it?
No, it's a open source. This
I
thing
know,
you
but,
can.
but you have.
We use managed one, but we also have a test cluster where we host it ourselves. So you just need a node and then run it as
Yeah, you could do locally or you could. I think we have like Confluent also provides
Yeah.
Kafka.
Yeah. They also provide managed services.
Okay.
All the major cloud providers provide a managed Kafka services.
Yes. So my question was regarding when you were saying multi-threaded, like one consumer can be multi-threaded, right? So in that, how do you acknowledge message? Because sometimes what will happen is that like one event will come, you will assign it to a thread, then another event will come, then you will start pulling for the other event.
No, so we wait for all the threads to complete their task before we pull for the next event. So we commit offset and only after that we pull it again.
Okay, so you're saying that like at a time, let's say you have 10 threads on that consumer.
Right.
When all these 10 threads have processed, only after that you will start pulling. Is that?
No, actually we pause all the partitions which we read from. So yes, we assign each partition to each worker.
At partition level I understand,
No.
but within one partition.
So we receive, suppose if we receive 100 messages, we'll group by all the 100 messages into 10 partitions. So we'll assign that 10 partitions to workers. Once that particular thread completes those partitions, then we'll poll for that partition.
So my question is,
We don't
do you have
publish
one thread per worker or
No,
do you have?
we have a main thread that commits to Kafka, but we have subthreads which execute the task. Once the subthread says this task is completed, then we'll resume that partition.
But how do you, okay, so I'm sorry if I'm taking the
No,
step, but
Yeah, can you first?
I can connect with you later. Like it's
No, if you see that,
Yeah,
we
this
have,
one.
we have a code of 2 active task.
I think it's easier that
It's easier.
because because there is only one main consumer thread which is reading, right? So once you read from a partition, and again, so there is only one consumer per partition, okay? Right? So once you read, you pause the partition until all the messages from read are consumed, and then you commit offset and then you resume again.
So when you poll again,
Yeah.
so do you get as many number of messages as you have threads in that consumer?
You can get more, it is
But
configurable.
do you, so if you get only one message and you put it in like one of the threads, the other threads will be like idle, right?
No, for that partition is passed, but from other partitions you can still read.
Yeah.
Okay, so you have this thread pool is also shared by different partitions.
Yeah,
Yeah.
you have a main thread that is connected to Kafka.
Mhm.
So suppose if I receive one message from partition 1,
I see.
So
I thought you had like one thread pool per partition, but you are saying one same thread pool for all the partitions.
yeah, that
Yeah.
is your thread per consumer model.
So
What?
you assign the partitions when you bring up the consumers, right?
I get it. I mean, I had a misunderstanding. Yes.
So yeah, again, so the comparison, there is thread per consumer and multi-threaded. Obviously, the first one is more simple, out of the box. You don't need to tinker around a lot. Less complexity, so easier to maintain. Can do automatic commit and rebalancing. Scale is limited by number of partitions because say if you go beyond that, you would be essentially consuming the same message twice, right? Suitable for less
You
idle.
are using Python, right?
Yeah.
So multi-threading support is for resource-intensive tasks. Multi-threading is not good in the how to use multi-threading.
So our tasks are actually IO intensive because we are writing to DB and fetching other records.
You are not processing.
We are,
So processing could be a resource-intensive task.
it is.
So in that case, how is multi-threading, like since Python has that global interpreter now?
No, so thread pool actually uses multiple pool of threads actually. So yeah, multi-threaded is more complex to code, test, debug and maintain. So what we have done is we have packaged our consumer in a separate module, and then the tasks themselves as a runnable Python classes. So any new developer that comes in, he just needs to manage his task runner rather than actually the consumer. Right. So that way anyone can come in and work, and it's more resource efficient because you are using all the available CPU resources, and then more control over how you process messages. Yeah, so if you are actually planning on implementing, there are 3 things you consider for both of them, right? Ensure that the records from the same partition are processed only by one thread at a time. And then commit offsets only after records are processed, because then the pre-commits are actually a pitfall for a lot of duplicate duplicate event reads, right? So yeah, and then handle the group rebalancing properly. So if you manage these 3, then it's up to you. Like depending on your use case, you can choose which one to implement and which one suits your needs. Yeah. That's it. Any questions?
Let's say we just have a particular topic, like just one topic. Now we have 2 partitions, so there will be 2 consumers. Now like, we receive one particular message which is taking too much of time to process for that particular instance. So it brings the instance down. So it has not committed to the Kafka. So still that message will be out there in the Kafka. Commit has not been updated. So again that second instance which is up, it will pick that message. Again it will go down. Now as both instances are down, so we will bring up another one instance. So again the same set of scenario happens. So how to handle that kind of things?
So you can make your process itself idempotent, right? Like make sure that you write somewhere else also that you have processed a log, a kind of log that you are processing this event and it has reached this stage.
Correct, but let's say still the producer will be producing. So again still the messages count in the Kafka will be increasing. So no matter what, like how many instances we bring up, still it is going to like take it down.
You have to set up alerts for like developer, whatever who is managing.
Yeah.
Like there shouldn't be this more.
So that would be a catastrophic failure, right? Like all your consumers are going down.
Because like we have to then flush the data right from the Kafka topic, like then only.
Why would you flush the data?
Then how can we
lost
You can't bring the consumer input step in Kafka so that you never lose it.
Yeah.
I can make a false commit to that message saying that I have read this message, assign it to a, send it to a different topic,
And then
DLQ or something like that.
DLQ, yeah, exactly. So instead of letting it fail, you catch it somewhere and then push it to DLQ and then process the next one.
set a specific time that within this time frame the message doesn't process, then you can send it.
You also need to handle
What did you
back
evaluate?
pressure.
I mean, apart from
There's something called
What
back
is it?
pressure.
Kafka alternatives that you have evaluated and
Back pressure.
you chose Kafka.
Yeah, that's
Mostly because we didn't want to lose the events.
handle for that.
We wanted to even see the orders they are coming, and then it's obviously fault tolerant.
Not handling of the
No, but there are other alternatives also.
RabbitMQ.
Have you evaluated?
No, RabbitMQ is just it's a message saving protocol, right? It's not as resilient as Kafka.
And AWS has SQS, SMS. SQS is
No, it's a single queue. It cannot scale up. And
SMS,
as
fan out.
SMS is again, it's like a subscription, this kind of thing.
I don't think it has
It's not as resilient, it's not scalable. Right? There is something called MQTT. Okay, so it's a watered down version of Kafka. You would use that to say to communicate or like send the data. It's a protocol which works on a cluster like Kafka. Okay, so essentially it is IoTs. So say you have a very little bandwidth to send data. So MQTT makes sure that the actual data reaches the destination, because a lot of our HTTP requests, right, they are inflated with the headers and all. MQTT strips them down, makes it to bare minimum, and then just sends it. So if that's something interesting, you can check it out. It's the same concept.
Yeah, that anyway it is a protocol. Ultimately somebody has to handle that.
Yeah, yeah.
But SMS, I don't think it maintains the orders. That's the thing that you're saying, right? Events maintaining the same order. I don't think it is.
SMS so you have to configure SMS mentioning that you need to maintain the order.
You can make it FIFO.
Then others.
FIFO, yeah. FIFO keys.
So basically, according to you, there is no other alternatives for Kafka.
As resilient as Kafka.
I mean, Pulsar is there. Pulsar is definitely there. I mean, Pulsar is a much newer thing that has been made by like pretty much the same folks.
Yeah.
But I mean, it is much more new. But Kafka is
Very proven.
like Kafka is like community is very big. Like
Yeah.
the amount of people that are using. Like we used Kafka and Pulsar both, and we realized that Kafka has far bigger support.
Support. It's been almost what, like 12, 13 years since Kafka was donated to senior student. So a decade of community is there to resolve your issues if there is a problem.
I think we have event hub also. Right?
Pulsar is more fancy. Like it was more fancy.
I think, yeah,
It is much
event
newer
hub is there and
community.
Service was.
yeah.
And STS you are saying you cannot scale as much as Kafka.
SQS, you cannot even have multiple consumers. You can have like multiple consumers groups basically.
Parameter business Kafka application better. And it has a wider community.
Yeah.
And the issue with RabbitMQ was larger payloads is the issue with RabbitMQ. We have heavy payloads, that is one of the considerations.
That's also